Hello everyone, welcome to my master thesis defense presentation. Let me first introduce myself. I'm Turhan Kargın and I'm from Turkey, and I'm holding my bachelor degree in electronic engineering. And this is my master thesis defense presentation from Poznan University of Technology. And so my thesis title is The Control of Soft Continuum Robot by Reinforcement Learning Algorithm. And my supervisor who helped me during my master thesis project is Mr. Jacob Bernard. So, well, now I will show you my presentation outline. Here you can see the topics I will cover during the presentation. I will first shortly introduce my main goal, and the introduction of the project includes Continuum Robot and the reinforcement learning. And later I will discuss my aims, and then I will finish with a conclusion. And this was my agenda, and you can see my progress and during the project, and there's four main steps, and also you can see the timeline. Currently this is 2022, and also here I put a figure for audience to give a small intuition about what is continuum robot. You can see that this is traditional rigid manipulators, and this is hyper redundant, and this is continuum robots. And you can imagine that theoretically continuum robots has infinite number of degrees of freedom. And now the main goal of the project is to first to model the continuum robot by using existing frameworks, and to investigate and simulate the advantages of applying deep reinforcement learning to continuum robot using the model that we created. And we use the deep deterministic policy gradient algorithm for as deep reinforcement learning, which is actor critic based. And because we use this because it can work in very large space and action space, it gives successful results for continuous action situations. And the idea of the simulation is to control a three-segment continuum robot by taking from a random starting point to a random target point. And here one frame from the simulation, and you can see that this is three-section continuum robot. Each different color is a different section. And this is the starting point. It's generated by randomly, and this is the target point. Also, it's generated by randomly in a task space of the robot, and by simulating the robot reach to the target point. And now I want to express my motivation to do this project. And many years researcher made very good efforts, very successful results in to make machines intelligent. And because they want these machines, these robots, to do human, boring human tasks, the repetitive, dangerous, or heavy works. And in traditional robotics, the control of robot is realized by establishing kinematic and dynamic models in the form of a transformation matrix mostly. And these traditional controllers give excellent results for traditional rigid manipulators, but it become really difficult to implement when we dealing with soft robots such as a Continuum robot that we used in this project. And you can see this how robots can have motion with different type of robots in this figure. And also the model of Continuum robot is even much more complex than traditional robots. And reinforcement learning theory was proposed for continuum robots, and developers try to apply it to continuum robots, and they see that it gives most of the time better results when we compare it to traditional controls. And here I give us a figure for to understand what is reinforcement learning. Basically, we have an agent, and in this situation, it's continuum robot, and it takes action. It moves in the environment, and environment gives a new state and a reward to the robot. And the aim is to maximize this reward. In the purpose of the reinforcement learning is to maximize the reward. And now I want to talk about what is continuum robot. It's a robot mostly inspired by the biological things like octopus tentacles, snakes, and trunks. And here you can see the elephant trunks, and there are many continuum robots which look like this elephant trunks. And also you can see here the classification of manipulators that I took from this article. And you can see here where the continuum robot belongs, and also it covers the soft robotics. And also the continuum robots can be very small because we basically have theoretically have infinite number of degrees of freedom, like, and when we increase the number of degrees of freedom, we can reduce the size of the robot. So here, like the traditional robots, they are very big, and the hyper-reductant robots, they are relatively smaller, and then continuum robots, they can be very small. They can even go to vessels of human. And also, when I was talking about the vessels of human, this kind of robots are very popular now in medical applications, and also some maintenance, repair, and operational applications. Think about the jet, the engine of the jet, and every time the jet will take off, the operators should check if there is something wrong inside some electronical parts and some mechanical parts. But as you can imagine, this inside of the jet engine is very, like, it's hard to reach everywhere. So if you have a very small continuum robot and autonomously going through inside of this engine jet and check if everything is all right, so this kind of application nowadays getting popular. And now I want to define what is reinforcement learning. Reinforcement learning is uh, it's array of machine learning, and you know that machine learning is one of the array of artificial intelligence. And machine learning has basic three paradigm: supervised learning, unsupervised learning, and reinforcement learning. And this supervised and unsupervised learning is working in more with data, but in reinforcement learning we don't need to have a data to do the project. It is different than this other two paradigm, and the focus is finding a balance between exploration and exploitation. It's somehow a trial and error activity, we can tell, and the main purpose is to maximize the reward. So this is a kind of a optimization problem. And here you can see a example of reinforcement learning in our nature. We can teach something to our dog via trial and error, and every time the dog achieves something, we can give dog a reward, for example food, so that next time the dog will do your task even better. And after successful attempts in other areas for reinforcement learning, such as games, the developers and researchers started to um, use this methodology in robotics, and it gives very successful results. It gave very successful results, and this method enables a robot to autonomously discover an optimal behavior through trial and error interaction with its environment. So after making some introduction, I want to tell about my aims. And one of the first aim is to model the continuum robot. And here you can see the two mapping structure of the Continuum robot. And our aim is to get task space, because in RL we will control the robot in task space. So we need to map the model to the task space. And here there is a even more detailed version of this mapping. And in this project, we didn't use the actuator space. We basically defined the curvature values and arc length values for our robot. We also didn't use the phi angle because we work with planar case, 2D case, so that's why we didn't need this phi angle. And when we map this configuration space to task space, we got the position of the robot, basically x and y. There is no z because we are working in planar case. And here you can see the units of the curvature and arc length. And here there are some different methods for modeling the robot. Among them, we will use a constant curvature representation. The reason why we use this method, because of its simplicity. It's very easy to implement. And here you can see the arc length, the curvature value. This is basically the radiator of this section. And to model this, we basically take advantage of this article here. I want to give credit. And so later on, after the forward kinematic modeling, we derived equations of velocity kinematics. And we use this because Jacobian matrix here are very super useful tool and heavily used throughout the robotics and control theory. Basically, Jacobian defines a dynamic relationship between two different representations of a system. And this relationship, in our case, is the derivative of position and the derivative of curvature. And in velocity kinematic, the target is to describe a motion of the tip of the robot. So the tip point, end point of our robot. The motion is highly constrained by curvatures, logically, which means describing the states of motion at those curvature is describing the motion of the tip point. So later, I want to mention the RL algorithm that we use is deep deterministic policy gradient. This algorithm is a deep reinforcement learning algorithm that can work in continuous actions with continuous actions. It combines the ideas from deterministic policy gradient, actor critic method, and the deep Q learning, and it uses experience replay and slow learning rate networks from DQNA, the DQN, deep Q learning, and it's based on the deterministic policy gradient, which can operate over continuous action space. So it can solve very large action and state space because it is using two separate neural networks for both action and Q value generation, action selection and Q value generation. And these neural networks are for function approximation of Q value and the action. So this is the diagram to show how we train the robot. So we have a continuum environment, and this environment takes action, and according to this action it moves, and according to this moves it generates a new state and new reward, and this state goes to actor, also critic. An actor generates action, also this action goes to critic, and this critic generates a Q value. And this Q value is basically criticizing our action, if it is good or it is bad. Also, to update, to train our system, we have a critic loss and the actor loss. So every time it tries to get even better action, so that having better rewards, so that it can maximize the rewards. So after training, we needed to test the robot. So this is the test diagram and how it is working. So basically we have a policy network, which is actor network, and this policy network gives us an action. I will mention, and this action is the derivative of each section's curvature, and then according to this action it is moving and generating a position, new position, and also it takes the target position because we want our algorithm to know where the target is. So basically there is a continuous loop here, and when the robot reaches the target it is terminated. And after now I want to mention some mathematical equations to solve the forward kinematics and the velocity kinematics. I will not go very deep here, but I want to mention about these mathematical formulations shortly. I mentioned we have a mapping, and I told you that we use curvature for each section and the arc length, and then we map to the task space. And here the heterogeneous transformation matrix that I took from the article that I mentioned here. Yes, here. And we defined this matrix for each section, and then we multiply them so that we have a position for each section. And but in algorithm I use just the tip of the robot's position, the position of just the tip of the robot, because it is computationally less expensive for the algorithm. As you know, we are working with two neural networks and it will take a lot of time to train, so at least we can have some less expensive formulation here. Also, that's why we used 2D robot, the planar case, as because we want to train our algorithm faster. And I give this mathematical formulation, this matrix, to the algorithm. Basically we just calculate the position of the tip of the robot, but at the end, to visualize the robot, I calculate each section's position, and so that it's visually looking better. And this is just an implementation for forward kinematic. You can see there's 3 sections, and each section has some different arc length and different curvature value. And just to be more realistic, we put constraints for our curvature values, and you can see the constraints here. And this is the velocity kinematics formulation. This is our Jacobian, and it makes the relationship between the derivative of each section's curvature and the derivative of the position. And to simply move the robot, we use this simple algorithm. It basically generates a movement for the tip of the robot, and this is the just simple figure that shows the trajectory of the tip of the robot when we use this algorithm. These blue points are the tip of the robot just moving and throwing this trajectory. And also this is the deep deterministic policy gradient algorithm. I will not go here deeply because it will take a lot of time, but if you want to learn about it, if you want to see how it is working, you can go this website. It's very useful, and you can understand how this algorithm works in a pendulum example. Here I want to show. This is a Keras tutorial. And now the most crucial part is the design RL environment. This is key point because we need to design a good environment so that we can achieve our goal. So the RL environment was created based on the kinematics from the previous slides, and we choose the action space for derivative of the curvatures for each section, and we have a basic x and y for instant position as a state. Also, we have x goal and y goal for states. We have 4-dimension states. And our reward is basically the minus error square. And what is error? It's the Euclidean distance of our position to the target point. It gives a meaningful reward because this is point-to-point access control. So this reward gives successful result. And then we made in the design, we need to analyze our task space for the robot. This is the main task space, so that when the robot tries to generate a random target point, it shouldn't go out from the task space. Otherwise, the robot can't reach this point. So we put our environment that this is our task space and the robot can't go outside of this range. And every deep learning project have some hyperparameter tuning session. Uh, in our case, this is the hyperparameters that we use that gives successful result. And as I mentioned before, we have actor and critic, two different neural networks, and the values are here visible. And this is the actor architecture. We have 2, 3, 4 hidden layer, and the first 2 hidden layer has 512 neurons, and the other 2 hidden layer has 256 neurons. And our input is states, and our output is the actions. And this is the critic architecture. We have again 4 hidden layer, and we have states and actions as inputs, and Q value as output. So I want to talk about my result now. So the 3000 episodes were used to train the algorithm and to perform a successful training. And we have maximum training space, which is 1000. So as a result, there can be maximum 3 million steps. But of course, it is less than 3 million because some of the episode robot reached to the target point and it is terminated before the 1000th step. And I have here the computer which has this hardware features. And with this computer, it took 14 hours to train these 3000 episodes. And of course, we use the NVIDIA CUDA infrastructure. It gives a faster result. And this is the after 3000 episodes. This is the moving average per 300 episode result, and this is the reward per episode. And you can see that error is after some episode, it's maximizing to the almost zero. It's converging to almost zero. And this is the mean error for the x and y axis. So it's all also converging to zero. This is what we want. And here there is a one video that I created, but sorry, now I don't have a connection. I think I will show you soon. Every time I run the script, it generates a random starting point and random target point, and the robot tries to go this target point. And as you can see here, it's not having successful results every time. And also I will later show the error graphics and also the reference signal and the position for the x and y axis. Sorry for the connection. Here now I will show the each position for x and y and the reference signal. And now I will see the error for the position. So now I want to conclude what I achieved. So first, the forward kinematics and the velocity kinematics for the Continuum robot was built, and then reinforcement learning environment was implemented. And for this environment, proper action, states, and reward functions were chosen. And then DDPG algorithm was implemented. And for this algorithm, an appropriate reward function is given to the environment to provide point-to-point control access control. And robot is going to the random target point from random starting point successfully after training 3000 episodes. And then future works will be implementing for other scenarios, and these are my ideas for future works. We can make some randomly moving target to, and for robot to track this. We can want for robot to track this, and or even some higher level control, for example, obstacle avoidance. Also, we can try to generate some other reward functions and compare them. And maybe the algorithm can be checked on real continuum robot. So thank you for listening to me. This is all.